From ContainerDays Hamburg, this video is proudly presented by Dax IT.
Okay, hello everyone. So as Melody said, I'm here to talk about securing AI ML workflows. So basically, how we at ChainGuard try to optimize container images specifically for Kubernetes environments. Some interesting problems, some struggles we're facing. That it's a difficult problem to solve. It's not fully solved, and it's a moving target. So it won't be just the solutions, but also I'll try to mention some of the problems and how we try to tackle them. And maybe I'll start I guess a little range to start. So here's my GitHub handle, my email. I'm also on the Kubernetes and CNCF Slack if anybody wants to reach out. And maybe I'll start by explaining how we build images and packages at ChainGuard. They're all open source tools. You can go check them out, but it's slightly different from how a lot of people build images. So we use two tools, one of them called Melange, the other one AppCo. So we have our own Linux distribution at ChainGuard called Wolfie. It's an open source distribution. It's on GitHub. You can go rebuild it. You can just pull it. It's right now it supports containers and VMs, so you can run it. I believe it's not officially supported, but we even run it on Raspberry Pis. It works fine. So the idea is it's somewhat similar to Alpine. We use APK as the package format. I'll explain the differences in a bit. But the idea that we use our own open source tool called Melange to package all the things. Then we use AppCo to build images from that, with the idea that when we build images, we just basically merge multiple packages into one or more OCI image layers. And maybe some more explanations to that, right? So as I said, Wolfie is a Linux undistro technically, which means we do not have releases. We keep on rebuilding all the things to be the latest versions of all the packages. So say we try to pull the latest glibc every day, we build it. If it works, then we start using it from that moment on. We use APK as the package format. We also try to compile with as little dependencies as possible where it makes sense. So say compared to Ubuntu, we would be trying to reduce some of the configuration flags and reduce some of the dependencies that we would ship just to make a lot of the things smaller. And we also, unlike Alpine, we use glibc instead of Muscle, which makes a lot of the problems smaller, and it helps with the performance in many cases. Like glibc is battle tested for a lot of things, and that's the default. So we would try to do that. So Melange is a really nice idea where we just build APK packages using declarative pipelines in YAML. You may think it's very similar to, say, GitHub Actions, where we also have reusable pipelines that you can invoke. And it can be used both with Alpine and Wolfie. We mostly use it with Wolfie, but it supports Alpine just fine. You just need to provide it with which packages it should be pulling, whether that's the Alpine or Wolfie as the base layers to build on top of. The example is too big to pull it here, but it's basically just YAML saying like go build or calling specific shell commands and doing git check out all the usual things you would do when you compile a package. And then we convert that into images. And like I said, the idea is we just take multiple APKs. We have some dependency resolution. So we say we need the base layout, which is the base file system that each image has to have, like, well, everything from LDSO to some files that you need in /etc. So that plus you can tell it, for example, pull GCC, and it's going to pull all the dependencies and just include that in the image. And the nice thing is building the images is quite fast, and it's basically not invoking any code. So that makes it a really nice separation. It's important because some of the things that we do rely on this idea, and also having packages defined in this way is a bit cleaner than having a large Docker file that's doing a lot of things. Plus, we can separate dependencies. So that helps us with some of the things, and it's worth mentioning. And again, all of this is open source. You can go play with that, and you can also use it with Alpine. AppCo also works with Alpine, from what I remember. So, and I think we even said this in the previous slide. Yes, AppCo also works with Alpine. So it's an interesting set of tools, but that's not really what I want to talk about. We came here to listen about AI/ML and me talking about it, so let's move on to that, right? So it's a lot of fun. One thing that's not in this slide is whenever I was trying to rebuild it on a very powerful VM in the cloud, it takes hours, so every mistake you make is a really painful one because you have to retry again 3 hours later, which doesn't give you a lot of time or makes you run some things on weekends just to catch up. Right, so normally when we think about containers, and this is some generic slide, like we think about portability, scalability, efficiency, isolation, reproducibility, and also like in my mind, most container images would be small, would be like easy to use. They would be, again, like isolation, like they would be just, just shipping the things that they need. Now, with AI, it's a bit different, right? So again, containers, you have small containers, very little dependencies. We talked about that, like at Jenga, we try to trim down the dependencies that come in from compiling things by reducing some of the options. And AI/ML is basically, it ships everything. So if you look at the default PyTorch image, it ships, I believe, 15 gigabytes, something like this. Maybe it's a bit smaller now, but when I was looking at it, it was quite big. And it basically ships, when you scan it, it reports thousands of CVEs. So it just ships half the internet, basically, whatever pip was just pulling at this point in time. And it's a challenge. Obviously, a lot of these packages are needed, but it is a challenge to maintain for us. And also, not only that, there's also the combinatorial explosion of all the things that should be supported. And I have to say, when I was working on this, it was a bit harder. Now it's a bit easier, but it's still, we have apps that support multiple versions, so we need to be building those. There are multiple versions of Python. We'll get to that in the next slides. GPU, CPU, like for example, I don't know. I think it was PyTorch that also has different logic for running on GPU versus CPU, or maybe some other tool. But like a lot of the AI/ML tools will have just completely different logic, completely different libraries they load. So if you run it without the GPU, you can't really test the GPU version. You can't really even test if it loads at all, right? So sometimes you need the GPU just to, I don't know, do an import and see that things import properly. So it's really challenging. And then on top of that, there's the hardware support. That's gotten better recently, but it's still a challenge because depending on which hardware you run it on, specific drivers support specific hardware and specific drivers support specific libraries. Again, that's slightly better now. NVIDIA partially solved it with their compatibility layers. But say 6-12 months ago, it was a huge challenge, especially with a lot of our customers still using the NVIDIA drivers on version 11, which really requires everything to be exact same version, and then we have to build with whatever our customers need. So that's quite a challenge. Hopefully this works. Yes. So I think I was trying to ask AI to render an AI/ML container, and I think it's a good visualization because normally the containers would be this small thing, normal thing. This was weird. This had a fan on top of it, and I kind of think the fan is this connection between the actual container and the drivers and all these weird things that have to be integrated between the container and the host, which you usually don't get with the regular containers, right? So the common problems and like the challenges that we face, and I think that we'll just drill down into things one by one, right? So image size, like I said, the goal of containers is you get something really small but still functional. And again, when I think about an Nginx container that should just ship Nginx, and a lot of the Golang world would just be shipping that one binary, maybe something like SSL certificates, but basically not a lot more, right? And then AI/ML is basically about shipping Python with pretty much everything that this package may need. And when you think about, I don't know, PyTorch specifically, it's going to be shipping a lot of things around audio, video, and I don't even remember the other libraries, but there's a lot of additional features on top of PyTorch that may or may not be shipped, and like that's one of the decisions that we have to make, right? So when I was working on PyTorch specifically, that was when the original image was 12 gigabytes, and by trying to trim some of the settings, some of the NVIDIA driver settings, and just basically trying not to ship the entire world based on what the packages needed, we got one of the images down to less than half the size, but it's still a lot, right? I mean, again, we can't remove everything. We can't just build bare PyTorch, have it 3 gigabytes, but not be able to do anything because you can't process images, you can't process audio. So it always has to be this these sets of things that we try to do. And then, like, when we started doing this, we didn't really have a lot of feedback from anyone using PyTorch. We just had to start by asking ourselves the question, like, what do we put in those images? And I think it was just I won't say a gut feeling, but I think it was a best guess based on how we at least knew some of our customers or some of the users were using it. And then obviously once we got some feedback from customers, we had to include some of the other things, but we tried to be disabling some of the things we thought would be used less often. And then if people asked us to include it, we would figure out a way to do this without, I don't know, creating two sets of images or without separating the number of options even more. So that's just PyTorch. But then, for example, when we think about more complex apps like Triton server, they ship PyTorch on their own, right? So then can we get the same PyTorch with the same sets of features to work with Triton server? And I think we ended up being able to do it, but I have not looked into this since for the last 3 months. I don't know if that hasn't changed, because one of the things in this area is that things change really fast, and I have not looked into this before this presentation that much. I looked into PyTorch itself. And right, so this is another problem, like how do we reduce the number of CVEs? And it's not that easy, and we're still trying to solve it as ChainGuard in general. So, right, so as soon as you start pulling in some apps packages and they include all of their transient dependencies, like you have a pile of CVEs that just try to enter your realm and then be including those images. So when we take that seriously, we try to ship images that have 0 CVEs or at least as little CVEs as possible, right? So in one case, by actually doing some smart logic in not just the image building, but also in some of the small tweaks in the requirements TXT, we were able to actually get an image that had over 1,000 CVEs all the way to 0. I don't think we can continue to like always have it at 0, but still, even if it's say 5 versus 1,000, any company that's going to be picking up this image, they're going to have a much easier time figuring out, okay, now I have to just create a report that we probably also will give them some, like we have our own advisory, so we would share some of the information we can share, like we think this is not exploitable, etc. They may also create their own vex files or anything like that to exclude it on their end, but like processing 5 versus 1,000 would still be much easier. And if it's 0, which is always our goal, there's nothing to process at all. But right, so Wolfie helps in that aspect. That's one of the things that we do. Like I said, for example, most images out there ship on top of Ubuntu, and sometimes that's Ubuntu 22, and then you would have over 3 years of packages that just have some critical fixes backported, but some of the fixes that aren't really exploitable in this aspect or aren't really worth fixing because they are an edge case that can't be exploited, like they would still be in the image, and that's how you get to those 1,000 CVEs. It doesn't mean they're exploitable, but it means anyone using that image has to go and analyze them. Either it's us providing that, well, if it would be us giving those images, we would go and provide those in the advisories. But if you're just downloading a PyTorch image and it has 1,000 CVEs and you're in an enterprise company, you're the one that has to write those reports, or you're the one that has to find the source to be able to exclude those, like explain those 1,000 CVEs. And then if you don't have process for that, whenever you update the image, you end up with the exact same problem of going through these CVEs again, and that's a lot of time, that's a lot of effort, either for you or for the security team. So it's not ideal. And again, rebuilding the latest packages of everything, like latest glibc, trying to rebuild it's not always possible to use the latest NVIDIA drivers, but that also helps, and it's easier now. And trying to build all the packages, like trying to use the latest Python, trying to use the latest system packages, that helps a lot, because these often have a lot of CVEs that aren't really exploitable or aren't really worth fixing at the upstream distribution without like Ubuntu, but by shipping the latest versions, we kind of avoid this altogether. And then again, we try to reduce what we ship in the images, and that's a generic thing we try to do with all the things. So then by not enabling some of the features and not having some of the transitive dependencies in the image, that also helps reducing the number of CVEs. So that's again, that's not a silver bullet. That's not something that's easily doable, but that's basically how we try to tackle this. And I think there is no good way to do this, right? The specifics of AI/ML workloads in general is like they bring a lot of software. They require a lot of software. It's also difficult to manage the host with the drivers. Luckily, with the public clouds, you're not the one managing them, but it's still a challenge to be doing all this. Right. So here's where all the things basically explode, right? So as I mentioned, like in one of the first slides, it's quite challenging. Like say just PyTorch, we ship PyTorch, but again, there's Torch Vision, Torch Audio. I think there was some other packages, like I don't really remember all of them, but basically you can enable everything or you can disable everything, and that's going to change what you ship significantly, but again, it's going to limit what the customers can do with that image, right? And then I already discussed version streams, which means that you could have PyTorch supporting multiple versions, like Python itself is version streamed, meaning that you have multiple versions that get released. Like Kubernetes is obviously a good example of version streamed software. You have multiple versions of Kubernetes being supported and released with EOL dates and with all the proper planning in place. So many AI/ML applications are like that. I don't remember PyTorch right now, but we ship a lot of them, and some of them, if they're version streamed, we're basically treating them as separate applications. So we would have, I don't know, PyTorch version N and Python version M, and they could have different definition how to build them. Oh, okay, that isn't good. Okay, that's back. Okay, right. So that's one thing, and then that adds up to the when you're trying to do the math for this. If you have 2 version streams and 10 options, it's already 20, and then Python, Python itself is challenging because some people may have code written that requires modules not available in some other versions of Python, etc., or not all the versions supported, right? So right now we ship less versions of Python, but in the past, now it's only 4 supported versions of Python. But when I was starting to work on this, it was 5 versions, so 3.9 was still supported. And a lot of our customers had some older code that they needed to run. So basically, we had to rebuild it with multiple Python versions. And we didn't build all the combinations of all the Python versions. It would just be too much. But basically, we would have packages where it would be a combination of the version stream of the application. It even doesn't even say it, but it would also be the version of the NVIDIA driver, the version of Python, and sometimes you would have like a name, whether that's or like variants, whether that would be something that includes all the features or just the essential features. So it would basically be a lot, right? So yes, so what we would like to do, right, is on the left side of the image, we just want to have as little tracks that we need to follow as possible. And I think we're slowly getting to that point where we try to figure out, okay, which things should we really continue to maintain, which things do our customers ask about, and what makes sense in the AI/ML world. And we're trying to also understand how it's used by our customers to help us with that. But what we used to ship and still ship is this madness of all the possible options, all the possible tracks that we have to follow. And right, so GPU, I mentioned that. It was one thing is GPU, CPU support. We do have packages where we compile them very differently for GPU and non-GPU support. We also test them differently. Like GPU support is a challenge. I'll mention that later. NVIDIA drivers, it's much better now. We only support 4 versions, and that was a big change that we've made a few months ago. But it used to be, like I said, with version 11, you have to be at the exact driver levels that the customer has. And then we would also support 8 versions of from 12.1 to 12.8, maybe not 8, but at least 5, 6. I think we never supported 12.7. But all the other ones we did because of how NVIDIA works. Maybe I'll explain a bit. So, like I said, up until NVIDIA provided their compatibility layer, which allows the NVIDIA, like the libraries we ship in the container to be newer than the drivers on the host. So now that's solved, and in many cases we can just ship the latest version, and that's going to be talking to the older drivers. But for a long time, you had to have the exact same NVIDIA drivers, or there was a map of which drivers work with which hardware drivers. So based on what our customers were using, we had to build something that would work for them, and we couldn't just ship the latest one, which was suboptimal. Now I can say, okay, I'm saying like now it's better, but it's still a challenge. We also support ARM, and the amount of things that didn't used to work initially on ARM, it's better now, but things between GCC, some other specific ARM CPU platform, like I remembered some problems we had with atomics, some other things that I would never thought of being a challenge, because NVIDIA has its own compiler that calls GCC, and then all of that didn't really work well initially, because I suppose NVIDIA didn't also think about all the edge cases in how people could be setting up their compilers. And obviously, because we build our own compilers from source code, we use different compile flags. Somewhere along those dependencies, things got bad, but we had to, for example, do some wrappers, do some if devs, and a lot of fun to make things compile. Now it's a bit better again, but if you look out there, you'll find a lot of drama around atomics, ARM, and people basically changing some include files and doing some other crazy things to even get it to build, and we had to do the exact same thing, right? So again, what we try to do, and we're trying to improve this all the time, is figure out what's a reasonable subset, figure out what works, what doesn't, and it doesn't say this explicitly here, but we're also trying to listen to our customers as much as possible and just figure out how do we ship little number of versions. Okay, back, and still allow everyone to run these AI/ML apps. Right, and then GPU itself. Yes, so this is the smoke test image from Wikipedia. I found it interesting. I had no idea where the smoke test comes from. It comes from how people used to test sewage pipes in the 19th century. But anyway, doesn't matter that much. So we try to figure out how do we test all these. Like obviously, if you ship half the internet, you can't run all the possible unit tests. You can't run all the tests. But we try to at least test the entry points, the commands, try to load things, and then again, because many things work differently with and without GPU, we can't just set up a kind cluster or K3s cluster locally and just see if it loads. We actually have to do the same test with GPUs. We're trying to get to the point where we test all these things in the proper cloud setup with a proper cluster that has GPU support. But it's really challenging to do this at scale, and because it's slow, it's expensive, and so error prone. So we're slowly getting there. It's improving all the time. We have a team, we have a group of people that are focusing on the AI images, and we're trying to be better all the time. Like I said, when I worked on this, it was worse. Now it's better. So hopefully we're getting a much better handle of this month by month. But we do have some automated tests. We had some regressions where we had to figure out how do we make them not happen again. But it's impossible to test all these things. It's impossible to test all the integrations. And in the past, we had to test it against all the drivers, which was a huge pain. But now with the compat packages in NVIDIA, we basically ship less variants, and we can test this more easily. There were a lot of interesting problems with ARM because not all the clouds don't properly support it, and there were a lot of issues around host containers. I think that's a separate topic. I don't like. You can find me. You can find me by the Chingar booth later, and we can talk more. But it's really problematic to test this. And again, not all the hardware that our customers may be using are available in the public cloud, because if someone has their own data center and they bought specific GPUs, they set it up in a specific way, then we don't have a one-to-one way to replicate their environment, and we just have to do the best things possible to get things working, right? And right, so the nice thing is, because we are separating building and testing and images versus packages, we don't need the GPU for building. So when I mentioned those 2-3 hours, I could just spin up a VM with, I don't know, like 128 CPU cores on Google Cloud, and I could just be having it built in 2 hours instead of a whole day, which is exactly what it would take on my laptop. So that's a good thing. And again, if I get some of the compile options wrong or some of the steps wrong, I have to run things from scratch. So it's a really tedious process, but at least to test it, I don't have to rebuild it. So that's good. And when we build images, because we also just merge things together, we don't need GPU for that either. We just need the GPUs for tests. So Ideally, we would want to just run the tests everywhere. In practice, we use 2 clouds for now, and some of it is manual, some of it is automated, but we do have all of that at least documented for the steps that have to be manual for now. Intel ARM, now we have a setup where we can test both of them in the cloud. I think now even in 2 clouds, but up until a while ago, we could only test it in one of them. Harder driver versions, like I said, I think that's much better now, but it's still a problem for some of the things. It's still challenging, and like I said, we can't set it up one-to-one, right? And then this is something that was interesting to me, and I had no idea about this until I started working on AIML. So yeah, once we finished packaging all these things, and we had some things we were testing locally, right? So we had something that we ran some basic examples of the internet when we didn't really understand it a lot. And then once we run some more complex examples with our image versus upstream images, we noticed that in some cases they were much slower. And one of the things that helped, and maybe we changed it, or maybe we figure out how to do this better now, is for some reason venv was a problem for us. So once we stopped using venv, we noticed that at least PyTorch was much faster. It was on par with what you would expect from other PyTorch images as well. So I don't really know why, but we realized that's the case, and we stopped doing this. And I think our goals would also be that we figure out some sort of benchmarking for some of these applications, because performance and like not having regressions in performance and in the speed would be critical, right? Because if we don't notice it, release it, our customers pick it up, and suddenly their workloads are, say, they take twice as much time to run things, then this is where we get into these problematic situations. And yes, that's all I had. So thank you. And I think now there's the time for Q&A. So the first question is, where do you put all the combinations, image, name, tag, somewhere else? That's a very good question. And right now it's in the tags. So when I mentioned like the app version, the NVIDIA drivers version, and Python version, they go into the tags themselves. But that's mainly because of how we do things and how well it's closer to how our customers would be getting the images. Because historically, we would be enabling specific images for our customers, so we didn't want to have 20 different image names. But that doesn't really, that's more of a technical thing on ChainGuard's end than anything else. So we just chose to have one image and everything in the tags. I think whatever works would work. What about AMD GPU support? Good question. I mean, we focus on NVIDIA because that's what our customers always ask. If we get enough questions about AMD GPU, we'll probably have to explore it. The challenge there is it's a very different, well, I mean, I'm guessing because I've not done the research at all, but I would be expecting it's a very different environment because we would need to figure out the alternatives to all of the NVIDIA packages. Like there's the NVIDIA compilers, there's the NVIDIA drivers, there's the host container connection with the runtime, and we would probably have to learn a whole new ecosystem that AMD provides to figure it out.
Still have a bit of time for questions, so if you want, you can submit yours.
And if you want to chat with me afterwards, I'm going to be going to the ChainGuard booth, which is just to the left from here, and I'll be there for a while, so you can also catch me there. Okay. How do we get started to play around with AIML workloads? I suppose that's a very good question. So we have our own images, but there's also upstream images for PyTorch, and I think NVIDIA also has a lot of images on their registry. I would say you need a GPU-enabled, well, either a VM with Docker and NVIDIA runtime for Docker, or a Kubernetes cluster with GPU-enabled, and then just spin it up there. I am not an AIML expert, meaning that I run some tests. I didn't develop any reasonable workload. So I would just say the easiest thing may just be spin up a VM with GPU-enabled VM in the cloud, set up Dockers to use the NVIDIA container runtime, and then you should be able to spin up. Okay. So what do we use for CV scanning? That's a very long topic. Like I would say I most often use Gripe, and that's where the zero CVs came from. I'm actually working in a team that's trying to enable vulnerability scanners and help them scan chain guard and Wolfie containers. So it's a very long topic, and reach out. I'm happy to explain. On the x86 side, do you just test with Intel CPUs or AMD as well? We use whatever is in the cloud. So I mentioned the clouds, that's AWS and Google specifically. I think they all just use Intel, not AMD. But if they would provide AMD, we would also test with that. It's just we use whatever the instances the cloud gives us. Which environment is more difficult, public cloud or on premises? I don't manage on premises. We only use the cloud just because we default to testing all the things in the cloud, because this way I can document it and the next engineer can spin up the same instance type and be using the same thing. So I have no idea. Our customers use both, and they say that they like both. So no idea. How often things no longer built yesterday? Oh yes, and do we cache dependencies? Do things end up behind a wall? That's a very good question. It's not specific to AIML. Things break a lot, but it's also because we compile things. So like I said, we like something that worked yesterday with the latest version of glibc may not work now with the latest version of glibc, or if we bump GCC or if we change GCC settings, things break. We have a team in place that's just monitoring that. We have SLAs for all of this, and we do see these things. We detect these things. We don't have a cache per se. I mean, it's APK. So if we say NVIDIA drivers are a dependency for PyTorch, if NVIDIA drivers stop working, we just pick up whatever was the last building version of NVIDIA. So we don't. So NVIDIA drivers breaking builds wouldn't break PyTorch builds, but if PyTorch builds break, then we don't just don't ship a newer image. And if anything breaks, if anything fails the automated test at the package or image level, they will also just not get shipped. So that's another thing. We also have tests in place all over to make sure that at least the basic things like importing works. And again, importing is challenging, but do you see improvements in the AI Python ecosystem to productive needs? I think there's some improvement. I think all the packages are also more mature now. When I started working this, it was 10 months ago. It was more challenging. I think, for example, ARM support is much better now. There's a lot of things happening, but I think it's still, because it's a moving target, there's a lot of new things, and all the new things depend on previous things. Like Triton server just depends on PyTorch, and I used to think PyTorch is big enough that it has to be on its own. And then I saw some images that would be like 50 gigabytes of basically shipping 3/4 of the internet now. So because of the size, I would say it's always going to be challenging. What benchmarks and remediation strategies, images for the AI images to be compliant? Right now, some of it is manual. We run some tests. We have some data that we compare against. We want to automate that, but it's tricky. Like I said, it's on our wish list. We would really want to have reasonable benchmarks, reasonable performance goals, where we don't ship if something regresses. We do this manually, especially when we do some major changes, like when we were doing the NVIDIA compatibility drivers. It was something we tried to do. And where do we store the ML, LLM models? How to fast load them? We didn't do large models, really. Like the main thing we run are some tests and some things that we got from people that were willing to share some of the, I don't know, test models that we have with them. So I'm probably not the expert there. I'm just going to be honest. I have no idea. Okay.
Yeah, big round of applause.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.